Oh, but one other thing too. My office number. Anyway. Oh, sure. Thank you. Good. So one thing I do want to do is let you know where I am in 147. Probably most of you know because you walk by. I have an open door policy. If there's something that you don't understand, something you want to ask about, if I'm sitting there, come on in. If I'm not sitting there, go ahead and put something on my calendar. Invite me. My calendar is public, so feel free to do that. This relates to the capstone class. There's a good chance you're in the business of graduating this spring semester, and you would be taking the capstone class. If you're taking the capstone class next semester, spring semester, graduating senior, send me an email and give me your name. I need that to look at class enrollment and what we're doing. So let's go on. So I get the fun about talking about gas chromatography. You've had the fundamentals of chromatography. You're working on LC at this point, liquid chromatography. And so I think some of you have also had the laboratory at this point, haven't you, on gas chromatography doing fatty acid analysis. Probably not everybody, right? Just as a rotation, okay, rotation lab. And so we'll give a little bit of fundamental and then a little bit of, end up a little bit of practical. How's that? You know, if you look at gas chromatography, what do you expect is the mobile phase? A gas, you bet. Not too difficult, is it? Stationary phase? What is it? Well, you know, you might say that because traditionally the process has been called gas liquid chromatography, GLC. There's never been a liquid in there, which is kind of funny to me. It is a solid material. If it were liquid, it would tend to run out because it's kind of put on as a coating, and it's a highly viscous material. I suppose it's like glass. Glass is a liquid, right? And it takes a while to flow, so maybe we get by with it, but it's a little disconcerting to me. So sure, there is a stationary phase, and we'll talk a little bit about what those phases are, what those coatings are inside of this column that you've seen. And so again, from a name standpoint, you might find gas liquid chromatography. I like GC, gas chromatography. Some people may talk about high resolution gas chromatography. That's all pretty much high resolution at this point. There was a day when it wasn't high resolution. What types of analysis are done by GC? Almost anything you can think of in terms of a food laboratory. Fatty acids, a good example. How's that for you guys? Cholesterol, any kind of gas. It could be oxygen. Oxygen in a package. How much oxygen is left? You flushed it. You wanted to get rid of it. It's a problem to you. How do you measure it? Gas chromatography. You may be working with a solvent. Ethanol is a solvent or a different extraction solvent. Is it pure? Water. You can do a water analysis by gas chromatography. Alcohol, ethanol, so talk about the distilleries, sugars, amino acids, vitamins, pesticides. But, you know, we can kind of go on through the many different types. And often we think about analyzing things that are volatile that will go into a gas, that will go into a gas phase. And we oftentimes then make a derivative of things that aren't volatile to make them volatile. And so sugar, for example, gas chromatography is used for sugar analysis. What do? We take that sugar that would normally just decompose on heating, make a derivative of it, add some, it can be silyl groups, it can be ester groups. If the molecule loses its polarity, it becomes volatile. So sugar is volatile. Sugar would evaporate. Sounds kind of weird, but it does in this case. So it's very, very broadly used and sometimes misused because there is a place for liquid chromatography. There is a place for gas chromatography where they both really excel. So because it has been used by someone for something, think about it. How's that? From a history standpoint, chromatography started in something like 1850, and another landmark in here, 1906. From gas chromatography, it really started theoretically in 1941, a theoretical treatment that we could possibly do chromatography using a gas phase. That was absolutely new, a new concept. The first gas chromatograph was built in 1952. So that's interesting. 11 years later, they figured out how to turn theory into practice. But that's kind of an interesting chromatograph because they had somebody sitting at the end of this column, and you'll get a vision of this later on, and collecting whatever's there and then taking over, adding phenolphthalein and titrating it. So that was your detector, collecting what came out and titrating it. Wouldn't get too far today with that kind of a detector. In 1954, the thermal conductivity detector came into being, so thermal conductivity. That's really the start of modern chromatography as we think about it today. It was a detector that actually worked and sensed things without a lot of trouble. The process and a little bit about the hardware. The sample is vaporized. If it isn't a vapor already, we have to vaporize it, put it into a gas, so it moves with our mobile phase, our gas phase. So that's typically done through heat. So it's heated to vaporize it. Passes through this column where interaction occurs, just like any other type of chromatography. Does your analyte want to be in that gas and moving through at that temperature? Or does it want to be stuck and dissolved in the stationary phase on the inside of that column? So where does it want to be? Of course, those things that don't really like that stationary phase, they whiz through. Things that like that stationary phase hang around for a while. And of course, we've got this whole gradation between the two. And hopefully, separation occurs. And then detection should take place as well. We have many different types of detectors. I'll just say a little bit about a few of them. Certainly not all that there are out there. So this is a diagram really showing a simple version of it. The next figure is a little more complicated version. What do we have? Well, we got to have a mobile phase, right? What we call our mobile phase our carrier gas. It's what's carrying our analytes through our column. So our carrier gas. Well, that's about 2,000 pounds per square inch. I think we need some kind of flow controller and reducer for this. We'll blow it apart. You know, maybe LC can deal 2,000 psi. We can't. So anyway, we got to have a flow controller so we can control how fast and what pressure this gas is under. We've got to inject against this pressure, and so we have a special injection port. One of our weakest points in this whole process is how we get samples into this flowing gas. And we'll talk certainly more about this as well. And here's our column. That column can range anywhere from 1 meter to 60 meters. 60 meters in length if you think about it. And so it can be very short. 1 meter can just reach from here to the detector, or it can be very, very long. And we do take advantage of the vapor pressure volatility of our compounds by putting our column in an oven. And we might start off at something like 40 degrees centigrade. That's warm. It's just warm. And then those compounds that really want to evaporate or want to be a gas at 40 degrees, they hang around longer. But then we start programming this up. Okay, now it's at 60 degrees. Well, those compounds that really weren't interested in moving at 40 start moving at 60. Those that wait until move around 100 degrees centigrade, 150 centigrade. So we take advantage of temperature. That's what makes this a really, really powerful separation technique. We take advantage of basic chromatographic separations, basic principles, plus we add volatility, boiling point, onto that. And there's only one technique that I'm aware of that's more powerful in terms of separation. So this is number 2. We've got a detector at the end of this. So again, what's coming out of that column, we've got to have some way to measure it. And of course, it generates some kind of a view, typically some peaks on the chart. This is now a little more complicated version of the whole thing. Now we just don't have our carrier gas, our mobile phase. Comes the same way though, so that goes like this. But we've got a couple other tanks here too, when we look at most gas chromatographic systems. What we've got is we've got an air tank and a hydrogen tank, and then the corresponding regulators and so on. And they come over to keep a flame lit. We've got a little flame over here. That's a flame ionization detector. I'll spend time with it, don't worry. And so our compounds come through here, go through our column, and they actually get burned in this flame. And it's kind of neat how it works. I'll give a hint. that there's a 200, I think it's 250 volt potential put right above here, a little collector ring at 250 volts, and this is grounded. And when we start burning organic compounds, there's some ions in there, some pieces. Electricity actually flows across that flame. If it's pure hydrogen flame, there's no electricity flow. If there's anything organic being burned, there is an electrical flow. So it's a simple detector and really one of our favorite detectors. So that's why we typically have a couple other cylinders sitting over here. So we've got something for our mobile phase, and we've got something for our detector in this case. We show a syringe as an injection. That's typically the way we get samples in. Like I say, we'll spend some more time with that, a syringe injection. Typically, it's done more commonly today with an automated injector. It's a robot that sits over there, grabs your sample, puts it in a tray, cleans out the syringe, draws up a sample, brings it over, injects it into the gas chromatograph. Much more accurately than we can. How's that? So that's kind of a little more image to that. So we'll kind of go through this system. So let's look at our gases. They have to be high purity. They're not outrageously high purity. I was consulting for a food company one time, and they were buying helium that was, clean to I think the 6th or 7th decibel place. And boy, were they paying money for that, like several $100s per cylinder, over 1,000 actually. And I kind of looked at them and said, I don't think you need that. I think something like a $100 tank will do you. But they have to be high purity. You can't go down to your welding shop, if any of you do welding on the side. Get great places to get gases, but you're not going to be working with their quality of gases. So they're high purity, not outrageous. That is the source of our mobile phase, or our mobile phase. And typically for that carrier gas, that mobile phase, we're going to use helium or we're going to use hydrogen. So this will typically be what we're putting through our column as a mobile phase. I'll talk about why we like one more so than the other. It has something to do with money again. Detector gases, I mentioned that already. The detector may need a special gas. It may need additional gases. And that really depends upon the type of detector you've got. As I said, for hydrogen flame, our workhorse, we're going to have hydrogen and air. But for some other ones, we'll have special gases, oxygen, methane, or some other gas. But for the most part, we're pretty happy with the three gases, the hydrogen, helium, and air. Our gas flow regulators, well, they are pressure regulators. And again, not welding quality. They're all stainless steel. These things, gas chromatograph, it's measuring things in the nanogram, femtogram range. A few femtograms, and you're going to see a peak. So if you're dealing with, again, low quality regulators, there's membranes in there, there's seals in there, rubber seals, and so on. They're going to be having enough contamination coming off all the time to always give you a chromatogram, whether you put a sample in or not. Needless to say, it creates some issues. So, okay, you buy a good quality regulator too. So good quality gases, good quality regulators. The flow regulators, well, okay, we have a pressure regulator to bring it down to something workable, the pressure. And our flow regulators, it determines the rate. How fast is our mobile phase moving through our column? This is, as I said, one of our problems, how we get samples into the system. We do have to inject them into a very hot zone. We have to inject them into, or let's say, I'll get it right, in a system that's under pressure. So we're injecting against pressure into a hot zone. And this is just a very simple one, the injector system. Here's where our syringe would go in. So it gets down into here. We push the plunger down and make our injection. So our mobile phase is coming in here. So this is, we got our gas coming here. Some portion is going to go out here. The vast majority will go down here and sweep our sample into our column down here. And again, we've got different ways to make this happen, but I'll mention probably at the end of tomorrow. I know we're not going to be able to rush this. We don't want to get done too quickly. So we'll spend some more time, not tomorrow, sorry, Monday. But there is a gas seal up here. We've got to keep that gas online, right? And so we've got a rubber seal up here. We've got another seal down here, because this is a glass tube inside of a stainless steel chamber. And so those two seals can be a place of leakage. And whenever somebody has a problem with their gas chromatograph, they're not getting out of it, it's anything out of it. It's one of the first places I look. You know, is our gas coming in here, going out the top? Is it leaking around these seals? So they're a very important part, how we inject our sample and how we vaporize that sample. These are different types of these injection ports, different styles for different purposes. What we typically run is a split inlet. And by a split or split injection, the columns that we use are tiny. And again, you've seen this if you've done the laboratory. When you do the laboratory, Cindy or someone will go ahead and open up the door and show you the column, or maybe you've got one sitting out there. These things are, less than a millimeter in outside diameter, so less than a millimeter in size. The inside is about 0.25 millimeters, so tiny, tiny columns. Our gas flow is extremely small. If we simply dump a sample in there we take a sample we can measure. If we dump a measurable sample in there, it would just swamp that column. It wouldn't know what to do with it. And so we say, okay, we need these nice small columns for a good reason. And so we're just going to maybe put 1/20th of what I injected. We'll have a split setup. So maybe 1/20th of what I injected goes into the column. The other goes out into the room. Maybe it's a 1/100th of what you injected. So this is the most common, a split injection. Tiny amounts of sample give us really efficient chromatography. Split less is when, boy, we're having trouble detecting things. We're pushing every limit we can to find what we're doing. We're going to have a setup where we don't split it and we live with it. That's called the split less. On column, oh gosh, I'm going to inject my sample into about a 200-degree port, and it's going to go poof. Well, supposing our compound doesn't go poof, it goes ugh, and we simply thermally decomposes, right? Not a good solution to it. So things that don't like that high temperature, we're going to have a system that we can inject into cold temperatures. And again, you'll see a system coming up where we inject into cold temperatures. So split, splitless, on column. There are other techniques. We can actually inject up to 1 milliliter of sample on some really novel injection systems. On those systems, you inject that solvent in. It's under low temperature. It boils off the solvent and then stuffs your sample in. As long as your sample didn't evaporate with the solvent, you're good. If it did, not so good. So you can temperature program them. You can do neat things. Just a lot of options in how you can do this. So this is getting a little more detailed now about this injection port. I just showed you before, I showed you this part of it, so the beginning part. And then I want to kind of show you this idea of the split injection. So we're going to say we've got our mobile phase coming in about 54 milliliters per minute. That's nothing magic about that. That's for our example, right? It could be 30, it could be 100. What the heck? And so let's say it's 54 mils per minute of gas is coming in. 3 milliliters per minute of that gas simply go through what we call a septum purge and go out into the room. They're just done away with. Why? Because that rubber septum up there, as I said, is at 220 degrees centigrade. It's giving off contaminants. Well, any contaminants that are given off here get swept out. So that keeps our column clean, keeps our analysis better. So of the 54, 3 go here. Okay, 51 is going down here. So we inject down here, our sample's down here. So 51 mils per minute are coming down the center of this glass tube. And this glass tube is an opening on the end, so gas can either go out a vent, a split vent, or it can go into our column. And let's say we have our pressures, everything set up so we only get 1 mil per minute going through our column. That's our mobile phase flow rate. So of this 51, 1's going here, 50 parts are going out here into the room again. So it's a 1 to 50 split. 1/50th of what we put in, injected down here, ends up making its way onto the column. 50 parts go out here. And so we set this up. What kind of a ratio do we want? Again, if we're really, really looking hard to find things that might only be 10 to 1, maybe we'd try to get only 10 parts coming out here. We've got to have some flow through here. We've got to have this plain thing cleaning out. And so we can't say 0 split on this system. And so we'll then use a small split. If we got a load of things, maybe I'm injecting a pure essential oil, buckets of stuff. Okay, I might have 1 to 100. I might have 1 mil to 200, 500 coming out here. So what kind of sensitivity do we need is the key word here. This is the split less injection. And so the way this runs, and we're going to set it up the same way, 54 mils per minute coming in here. And what we've got is 3 mils of septum flow. And again, we should have more gas coming down here. But we really change it. So we more or less shut this off. And so instead of the 3, we've actually got 53 coming out here. So there's the 3 mils of septum flow plus the other 50 mils of gas that would normally be coming down here. So we make our injection into here. Our sample expands, goes from a liquid to a gas. It expands. But it's still, there's no place for it to go. It isn't going to back up here normally. It's going to be pushed down here. And for a certain amount of time, we'll allow all of this thing that we volatilized in here to creep into this column. And so we'll be putting as much as we can of what's here into this column. But we still have to clean this out, or our peaks will be that wide. And so we've got to clean it out. So we let it maybe run 1 minute and suck everything in there we can. After 1 minute, then we change our flow. So now we're cleaning the system out, and we got a nice clean injection port. Our injection's done. Again, if that doesn't make sense, you can ask Cindy and have her explain it to you when you're doing the lab, or stop by. How's that? Two most common injection ports. Here's our on-column injection. That's a cold injection. So at this point, we want to put our sample into a cold environment and then slowly heat it, so it's not going to thermally decompose. So here's our, well, we'll have gas coming in here. This will be our carrier gas coming in, so it's coming in here and coming into the column, so it comes this direction. But we have cooling air, so we got cool air coming around, so it keeps this part cold. Our syringe is one heck of a long needle. The needle may be that long and very, very fine diameter. And there's a little rubber valve here that the syringe can actually go through, then come down, come down, come down. Push the handle on the syringe or the plunger on the syringe, it injects down here, a cold area, then it can be warmed up with the column. So just for heat-sensitive materials. So those are the 3 most common ways of getting a sample into a gas chromatograph. Split injection, got a lot of material, no problem detecting it. We get nice, clean, quick injections that give us really good chromatography. The split less injection, we're looking for trace amounts of material. We're really searching. And we dump as much onto the column before we sweep it out and get the chromatography going. On column, we're then looking for heat sensitive, or looking to keep heat sensitive materials intact. So that's the injection. Where does everything go? It goes into our column. And it's, I think we have to go to one of the museums these days, although you will find a glass one sitting out by the flavor lab that's still sitting there. It's on its way to disposal. This happens to be a stainless steel column. Back in the olden days, that's what you'd have. You've had a stainless steel column, typically 1/4 inch in diameter, which is massive by our standards. And it may be 6 feet or 8 feet long. And that's, we coil up here. Inside of that is a granular material, our stationary phase. So there's a granular material that's coated with material that's going to be partitioning. It's going to go between that coating on this granular material and your mobile phase. So long gone, you'll have trouble finding them, which is good. Here's our nice capillary column, what we use today in all cases. Like to say, this is less than a millimeter in outside diameter, and it could be anywhere from 1 meter to 60 meters in length. So tiny diameter and a good deal of length to it. Normally what we do is we coat the inside of this column. It's what we call an open tubular column. That tube is open. There's no packing, no granular material in here. It's just this long, thin tube that's got the coating on the inside. Your stationary phase is coated on the inside of the glass. Sometimes they'll put kind of really, really fine material and fix it in here as a granular material, but it's really special applications. Most of it is just a tube where the walls are coated. All the interaction that occurs between your analytes and your stationary phase is with that coating on the wall. But remember, it's so tiny. This column is so tiny. There's not much of a distance between where the molecules are, even if they're at the center of the gas flow, and that wall. So they interact really, really well in this small tube. If we were trying to look at interaction on the wall here, just coat the wall, forget it. We have, there wouldn't be any interaction here in comparison to these tiny, tiny columns. So generally we're talking about open tubular columns. It's an open tube. Unique things, porous layer, open tubular. That's where the granular material is put on the inside, coated to the wall. The columns started off being stainless steel, then they went to Pyrex glass. Ultimately, they've gone to fused silica. And that's what we use today, is a fused silica column. They're so small. Cynthia, did you take them out and tie any knots in them or anything? Okay, good. Did you intend to light it on fire? Yes. Okay, good. Good. That's good to see. Okay. As long as no students were hurt. Okay. It's fascinating. You've got glass, and you can actually tie it in a knot. It's partly because that glass is so thin. You think if you got a big column, if you bend it any, that edge lifts up a lot. It's a lot of stress on it. But if it's really, really tiny, you can bend it. It isn't much stress in comparison. So extremely clean, high-quality glass. I think it's well over 2,000 degrees centigrade to melt it. You think other glasses melt well before that. So it is this special glass, strong and inert. The inside diameter will range from 0.1 millimeter to 0.53 millimeters. So we're talking about micrometers in terms of size of these things. Length 1 to 60. Yep, and here's where we put a coating on the inside, and that coating is actually very thin too. Anywhere from 0.1 micrometer to 5 micrometers. And we typically work kind of on this lower end of it. So very, very thin coatings on a very tiny column. The fact that it's flexible has a great deal of value to us. We used to take big glass columns and try to connect them to stainless steel. 1 out of 5 times it would break. That's a problem with connecting glass or metal to any kind of, connecting glass to any kind of metal is a problem. So let's go ahead. So what do we put inside of that column? What's our stationary phase? Back when I started, we had over 300 different things that you might put inside of this column. 300 different materials. And at this point, it's come down to 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different materials. And so those 9 have replaced the 300 that we used to use. The main reason for this is that when we didn't have very good columns, thin columns, high quality columns, we had to do a lot of separation by this coating. But once we get so efficient in our columns, we can kind of say, well, gosh, this will do much more than it used to. And so these 9 really do what 300 used to do, which is a real advantage. And they range from extremely non-polar dimethyl polysiloxane, so silica with methyl groups off the side, polymers. Really good for any kind of non-polar materials. Here are some column names out here. OV1, that's just a trade name for it. SE30, another trade name. but every company puts their own name on it. But they'll generally say something 1 or something, you know, it could be adjuvant 1, it could be variant 1 or whatever. But so you see there's names and numbers, and usually the numbers tend to be consistent across companies. So extremely nonpolar to very, very polar down here on the end. So very polar materials. What do we use? If we've got a bunch of nonpolar materials we want to separate by gas chromatography, we use a nonpolar column. We want some interaction between that column and our analytes. If we're analyzing polar materials, then we'll use this kind of a column because it really has a strong interaction with polar analytes. So, and a nice range in between. So we put a coating inside, and that's our stationary phase. Cindy? Yep, fatty acid, methyls. Mm-hmm. Yep. Why, when all 3 of them will do it? Yeah. If you have a really, really tough separation, you want to separate isomers, cis strands, you want to separate closely related fatty acids of really tough, complex mixtures, you're going to be working with this. But that column isn't very stable. It'll last a year, 2 years, and then you got to spend another $600 on another column. Okay, it does the job for you. You may have to use it. But if you're doing a fairly routine analysis, our normal fatty acids we come across in plant materials, whatever, we can probably get by with one of these other, and they're more durable. These things, you can do almost anything to. I'll take them up to 400 degrees centigrade. 400 degrees centigrade, not too close. I'm getting close to ashing, actually. And they're fine. You know, what happens to silica? Not too much. And so they're extremely durable. So you like to work with them if you can. But if you can't, then we go down here. So it's how complex is separation, really, is what bases it on. And again, I'm not knowing quite sure what we're going to come up with in class, right? We do the best when we can, the most. This. Mm-hmm. Sure. Well, they're esters. They're not just hydrocarbons, but they are esters. So they're something esterified to something else. And they can be fairly long hydrophobic. But those ester groups are polar. And everywhere, you know, the more ester groups in that polymer, the more polar it's going to become. But it is a compromise. You'd love to use some other things, but that's the most stable and the most polar we can use. Nobody really likes to use it, though, because it is labile. It does die a terrible death at $600. So how do we know what column to use? Well, that's always a good question. We have a system called the Kovats indices. And you may call it Kovats indices if you come from Europe. It may be if you happen to be an older person. So we won't say much more about that latter part, but they may call it retention indices instead of Kovats. Kovats was the inventor. He basically came up with this idea, but it goes back to retention indices. And so let's say this, you run a gas chromatograph. So here's your solvent coming down. And you're really interested in what is this compound? I want to know what that is. And so what you do is you mix your sample with some hydrocarbons. Maybe it's a C5, whoops, C5, C6, C7, C8. And so that's, pentane, hexane, heptane, and so on. And so when you mix them together, you find, oh, my compound I want to characterize, I want to identify, gee, that runs between hydrocarbon 6 and hydrocarbon 7. And I can kind of interpolate between the two, and maybe it runs at 6.82. So it's between 6 and 7. It's close to the 7. I can go in books and I can look that up. And what might that be? And also, it gives some idea of where things elute, where they come out in your gas chromatogram. So one way is to go ahead and look up where things elute on a given column. So going to a reference, that's a data log, a database, I should say, that has this. Journal articles, yeah, certainly. There isn't a lot that hasn't been done in this world, that hasn't been looked at by someone someplace. And again, thank the internet for making that broadly available to us. So journal articles. The thing to always keep in mind, though, is that because something's published, because it's peer-reviewed, doesn't mean it's the best approach. It doesn't even mean it is the best approach, but that's where you start, right? You start with that. So journal articles. If you're working in a company, oh gosh, maybe somebody in a company's seen it before. Hopefully they have a good retrieval system. They have a good way of keeping track of what they've done. And someone that's there or someplace in their archives, they'll say, oh, we've seen this compound before. This is what it is. So you kind of look out for databases. You look in published literature. You look in-house. If you don't find anything here, it's something about intuition. If you know anything about the molecule or where it came from, you might know this is a very nonpolar compound. It doesn't dissolve in water. It's nonpolar. Oh, I better choose a nonpolar column. If it's very polar, dissolves in water, you might say, well, I should use a carboax or something like that. So this kind of gets you into the category of well, let's make a good guess. I don't have anything else to go on. If you have no idea, then you pick one of those nonpolar columns, because like I say, they're rugged, they're durable. You can inject into them and, like I say, run it up to 400 degrees centigrade. If it's volatile, it's going to come out. You're going to at least find it. If you put some compounds on the carboax, they'll never come out. They just end up staying in there. You can't heat that column high enough. So the idea, get all the information you can about a sample, run it on a non-polar column, and change to polar if needed. I know one day I was at work and I had somebody carrying in a piece of drywall from their house. And they said, it stinks. Could you help me find out why it stinks? Oh, that sounds interesting. Sure. What do you know about it? Well, it's in my drywall. Okay. So you do it. You do some extractions of it, and you smell each of the extracts. And this one extracts the smell. You concentrate it, you clean it up, and you run it on the gas chromatography. You don't have the faintest idea what it is. So you start off with a very nonpolar column. We have our gas chromatograph set up so you can sit and smell at the end of them. So at the end of the column, a little bit goes into a detector. The rest of it goes to you sitting there. You're the detector. And so when you get that smell, you say, that's it. That's what I'm looking for. And then you go to other techniques. But it's a fun area. Okay, chromatographic processes. So you probably have gone through this, right? You've talked about adsorption chromatography, molecular exclusion. So who wants to define adsorption? What is adsorption chromatography? Someone want to volunteer that?
Is when a substance on the surface of a catalyst, metal catalyst.
It wouldn't have to be a metal probably, but yeah.
I was thinking like a glass.
Yep. Well, it's a good example though. So it's more of a surface phenomenon bonding onto a surface phenomena. More so. Molecular exclusion, what's that? Who said? Who what? Size exclusion, sure. How does that work? What's your basis of separation? It's a separation based on primarily size. size of the molecule, sure. So you separate on the basis of size. Here, this one's more for affinity to a surface of some kind or some part of the surface. Molecular exclusion separates on the basis of size. Have you done any partition chromatography? Your instructor is being frustrated here. She's a very competitive person. I would suggest somebody volunteers. We were playing bocce ball yesterday. We did okay, though. Only due to... I know. She said, if we lose, I'm not sleeping. Anybody want to offer what partition is? Sure. Typically, yeah. Yep, partitioning. You partition into between two different phases. And so in gas chromatography, we can take... Does he get a star for that?
Yeah, he's getting one.
Okay, good. So we take advantage of, one of these typically, more so one of these techniques. Then we add vapor pressure on top of it. Like I say, that's what gives us power. And I think I've probably already explained the idea that if something isn't volatile or isn't very volatile, it's going to have a tough time getting into that gas phase. So we separate based on boiling point volatility. Because we'll typically, in the orange oil analysis we're doing, we're starting off with our column at 40 degrees centigrade, and we warm it up to 200 degrees centigrade. And within that time frame, that temperature range, we force more things into that mobile phase. So we take advantage of one of these, plus always that one. So let's see. Oh my gosh, we're running behind, aren't we? I may have to take longer time. So, we talked about these, the polar, the non-polar columns, carboax, and so on. So we can go by that one. Okay, and we do have this oven. Like I say, it's inside of an oven. Our column's inside of the oven. And actually, it can go all the way down to minus 60 degrees centigrade, up to 400 degrees centigrade. So we can cover a broad range in volatility of compounds. And we do have things that are have volatility in that low temperature. Hydrogen sulfide, for example. I'm interested in hydrogen sulfide. It's an eggy smell. It flavors my bag. So now we can't get done, but we'll just get it started. How's that? What are the detectors? What are detectors for? And basically, we're going to change or turn the presence of an analyte of a column into an electronic signal. This is going to use all my time up. I may have to have another day, Pam. So yeah. So as we get things eluting, we want to turn it into some measurable signal. That's basically what our detectors do. And so, like I say, we've got several different detectors. What we'll do in the next class period is we'll talk about those detectors, talk a little bit about troubleshooting what can go wrong, and then some examples. So that's what we'll cover on Monday. So have a good weekend.
At this rate, Gary.
No. Remember, you had the beginning part.